Thank you for joining us today. Looks like Pittsburgh outside. I brought it. Today is the John Patrick Clisine lecture. Pat Clisine did his undergraduate at Carnegie Mellon University and got his PhD from my alma mater, the business school. Had a distinguished career, ended up being served as Dean Provost at Carnegie Mellon, and then the president of Georgia Tech. Made a lot of changes at Georgia Tech, including the founding of their School of Computing. He was very active in the Atlanta Olympics, had a distinguished career as a scholar and a world citizen, and we named the social science lecture after him. The Clisine lecture today will be presented by an equally distinguished scholar, John Lehoczky. I just asked John a question. I said, how long did you serve as a dean? 14 and a half years.
Amen.
The Dean of Humanities and Social Sciences, which became the Dietrich School when he was the dean, and a gift from the Dietrich family. When I came to Carnegie Mellon, as I was looking at the editorial board of management science, it was the first time I saw the name John Lehoczky. He was the area editor. He's pretty much served in every meaningful journal in some editorial capacity throughout these 30 plus years. His main teaching and research interest involves stochastic processes. During the past 5 to 10 years, I forget the years, he's become more interested in financial markets and real-time computer systems. Today he will talk about one of these topics. I forgot which one we should. There were two candidates. It's a pleasure to present to you Dr. John Lehoczky.
Thank you, Ilker. Okay, I see I have my own Pat Clisine slide. That's Pat. I knew him well, and you knew him well. He, just a word or two, he was really the individual who made what was then HNSS and what is now Dietrich College into a research unit that now is on par with all the rest of the university, and in fact beyond par with a number of places. He started the IS program, and of course we have an IS program here. He brought my home department of statistics into HNSS. He created philosophy, the philosophy department, and social and decision sciences, and now many of these are top-rank programs internationally. So it's a pleasure to be the Clisine lecturer today. Now, I'm talking about real-time systems, real-time computer systems. It's a technical topic, but I'm trying to skim the surface and make it interesting and make it accessible. So you can tell me later whether I succeeded in my mission or not. I've had a huge number of collaborators. Some of the key ones are listed in this. You don't know any of them, but I may mention their names from time to time throughout the talk. So I intend to just talk a little bit generally about what real-time systems are, and then I want to talk about three particular applications of them. The Mars Pathfinder rover, an interesting vignette in history. Autonomous vehicles, that's everything from drones to driverless cars, and things like video streaming, all of which are real-time systems and all of which this work applies. And then I want to describe at the end some work that we've done that I think will have some impact going forward. There's a small descent into technical stuff. I'll give you an alert You can doze off, and I'll try to wake you up when we get into something that's a little more interesting. So there are two different kinds of systems that I'm talking about here. One is like a self-contained device, like the Mars rover or a driverless car, a system, and that device, think about a driverless car, it can better be able to perform multiple tasks. For example, if you're driving 60 miles an hour down a highway, it better be able to detect that there's an obstacle in front of you and take some kind of evasive action or stop the car. So there are lots of things going on, all of which have to be processed simultaneously, all of which are time critical for safety. And basically, this device or system there are lots of tasks that could be running, depending on the circumstances. If you're sitting in traffic or if you're steaming down the highway, lots of different tasks can be there, and only a subset of them are running at any particular time. A different kind of application that's more akin to this video streaming idea, they're called queuing systems, and they're arriving demands to the system. And I mean, you can picture yourself in a waiting line for passport control. So you line up and wait your turn. That's a standard kind of queuing system, where you make calls to a call center that has to field all this information and give you responses. Or web servers that handle customer browsing on the web or things like movie streaming. Now, real-time systems arise when the tasks that you're dealing with have explicit timing requirements. And the example, again, is traveling at 60 miles an hour. There's an explicit timing requirement for the visual system that is detecting objects in your path. Or if you want to have an enjoyable movie experience, you don't want to see a little blast of a movie and then see that circle spinning around, and then you wait and get a little more blast. That kind of discontinuity has to be, is what interrupts a good movie experience. Queuing theory is a huge field. There are probably 100,000 papers in the literature. And most of them come down to thinking about the customer. What kind of experience is a customer in this waiting situation having? And so the metrics there are waiting time for your service. And then there's, from the server's point of view or the system's point of view, it's the efficiency of the system. So what percent of the time is the system busy and what percent of the time is it wasted? You know, how many servers at a call center do you have in order to give decent kind of response time? For Mars rover, driverless cars, these kind of closed systems, they have many, many explicit timing requirements, and there's a technical distinction between hard deadlines. It means it absolutely must be met or the system fails, and soft deadlines, which are more akin to the movie experience. So the human eye, the human perception system, is able to cope with these slight interrupts that might happen. But there's special performance metrics for those real-time systems that are unlike standard queuing theory, because there the focus here is on what fraction of the deadlines that the system is dealing with are going to be met. It's not necessarily the efficiency thing anymore. Now, when I think about the Mars rover, that's representative of a class of systems which have severe weight and power and space constraints. There is a limit to the amount of computing power that you can put on something like a Mars rover. And there's a rule of thumb you may not be aware of, but for every unit or, let's say, pound of computing power, it takes 4 times that number of pounds in order to provide sufficient power to the computer and sufficient cooling to the computer. So there's an enormous amount of extra overhead. And in these small systems like Mars rover International Space Station, GPS, Global Positioning System satellites, autonomous aircraft from drones, submarines, and now driverless cars. There's a limit to how much computing power you can use. So there's an importance to be able to share that resource as efficiently as possible, because you just can't load the car up with a ton of computers. Normally when you hear the word real time, it's synonymous with fast. Real time, fast. But for me, it's much more than that. It's a matter of having a scarce resource, the processing power, and sharing it with lots of different tasks and making sure that all of those deadlines or timing requirements are met. So you want to you have a limited number of computing cycles, and you have to use them as efficiently as possible. And when tasks have deadlines, and they have to share this common resource, then the traditional kinds of scheduling policies that are used, one is first in, first out, or FIFO. That's wait in the passport control. You just join the line and wait your turn to get to the end. Or something like processor sharing, which is a very common kind of scheduling algorithm for web servers, where there are a ton of requests that it's fielding, and it's kind of simultaneously dealing with all of them. Each of them is getting a little blast. So, but those things don't even look at the deadlines. There's no attention paid to that. So they're not really relevant here at all. And so our work has been focused on scheduling algorithms in this real-time context that do pay attention to those timing requirements, and then implementing them in the operating systems. So here's the alert, first alert. It's a small descent of slides into just a little bit of formal detail, and we'll come up for air in a couple of slides later. So this field, really, this most seminal paper was in 1973 by Lew and Leland. Lew was a summer student at the time at the Jet Propulsion Lab, and he dealt with exactly this problem. It had to do with space. And the way he thought of it is that imagine there are a bunch of independent tasks that a single processor has to deal with. And there's some number of them, and just some arbitrary number of them. They're called tau 1 to tau n, whatever they do. They're periodic, means they're repetitive. They keep coming back in like the clock. And these T's, this is what's called a worst case analysis. So these T's are the soonest it could ever reappear and ask for more service. And then there's C's, which is how much work or how much time it will take to satisfy the request that it's making. And these C's are the largest amount of time it could ever want. Okay. So you have largest amount of time it needs and the soonest it could ever come back. And in this paper, they thought of it in two ways. You can do what's called fixed priority scheduling, which means every one of these tasks is given a priority. And when some task shows up for its turn and has a higher priority than what the system is currently doing, it preempts and goes right in and gets service, kicks the other guy out. Dynamic priority is where the computer looks at the current set of work it has to do and makes a brilliant choice about what it should be doing next, okay, depending upon some criteria. And they asked the question that if you gave a collection of these CITIs and you were dealing with either fixed or dynamic, oops, I did wrong, fixed or dynamic scheduling, how could you tell that the computer would then be able to meet all those deadlines? Okay, so now I'm messing up my slides here. In the fixed priority case, they determined what the best scheduling algorithm could be. It's what's called rate monotonic. But basically, it's a very simple idea that the priorities are assigned. The TIs are the soonest they could come back. The one that's coming back fastest is the one that has the highest priority. The one that's coming back, coming slow, more slowly, is going to have a lower priority. And so that's the way that's the way the priority should be assigned. They figured out that no matter what you give to the computer to deal with in this periodic fashion, if you compute the utilization of this task set that you're giving it, that's the utilization of each of the tasks, if it's less than this odd-looking quantity, then it doesn't matter. You don't need to know anything else about this task set. It will meet all the deadlines forever, no matter how they're arranged, whatever. And if Murray and Oliver were in the room, then I think his calculus students would be able to handle this. That if there's one task, this odd-looking expression is equal to 1 or 100%. It means that if there's only one thing to do, it will always be able to do it. If there are two, then the worst thing that can befall you, it's 83%. And as there are more possible tasks, there are more possible situations, this bound keeps going downward. But it approaches a limit. It descends down to a limit. If you have an unlimited number of tasks, it's log 2, which is just about 69%. So if the utilization of any task set is below 69%, you have an absolute guarantee that all these deadlines will always be made. On the dynamic side, they proved that the best way to decide what you should be doing now is called earliest deadline. So whichever task is nearest to its deadline, do that one. And if you systematically do that, then actually, if the utilization of the task set is less than 100%, which obviously is the most you would ever let it be, then it's guaranteed it will meet all the deadlines. And obviously, 69%, which is the fixed priority number, is less than 100%, and so it would seem that this earliest deadline or dynamic idea is obviously superior. But there's a problem because, in the dynamic scheduling, if anything were to go wrong in dynamic scheduling, you can risk an entire cascade. And so suddenly, it could be that everything misses. If one thing misses its deadline, the whole sequence of things could miss their deadline. Whereas in the fixed priority, it's only the low priority guys that are ever at risk to miss their deadlines. Okay, so that's end of alert. You can wake up now. And I want to talk about applying this in the first context. So on December 4th in 1996, NASA launched what's called the Mars Pathfinder and rover project. It did the launch, and it was scheduled to land on Mars on July 4th, 1997, which for the U.S. folks in the audience, that's a magical day in the United States. It's Independence Day. So it was sent to a particular location because that was one that was thought to maybe have fluid and hopefully water, and it was going to do exploration in this area to see what the surface of Mars looked like. And it was programmed, it's scheduled for a 30-day period, and they thought that the power supply would be gone by then, even though it had solar power. It was only going to go for 30 days. So what happened is the flight to Mars worked absolutely perfectly. The landing on Mars, I'll give you a picture and describe it in a minute, was a huge success. And on July 5th, it landed on July 4th. On July 5th, the Pathfinder sent back pictures from Mars. And these were on the nightly news. These were on the top of the fold in the New York Times. It was a huge, huge success. Banner headlines in the New York Times. And at that moment in time, this kind of captured the U.S. imagination for a 2-day period. Because if you think back, familiar with U.S. space exploration, NASA had suffered a huge loss in the Challenger disaster. We were shooting astronauts into space, and it blew up and led to death, particularly of Judy Resnick, who was a CMU alumnus. So this was a marvel, And here are a couple of pictures. I'm not quite sure you can see this. This is the rover itself, and this is the Martian surface. And this one, I can just say a little bit more about it. How it landed on Earth, it was like a giant cocoon. Inside this cocoon was the rover. And so basically it hit Earth, it hit Mars and bounced who knows how far and came to rest. And then when it came to rest, eventually this cocoon opened up and you have this device. And this is actually a little ramp that rover I just showed you rode down onto the surface of Mars. So it's a miraculous engineering feat that worked absolutely spectacularly, perfectly. And then began to send pictures back. So immediately we had a great success. They tested all of the tasks that it would have to do, and then they had this 30-day limit, and so they wanted to go into full operation. But before I do this, I've had a couple of dinners, and the movie The Martian has come up. I don't sell tickets to movies, but it's a fabulous movie, really. I highly recommend it. And Matt Damon is a great performance in this movie. If you don't know the story, it's a different exploration of Mars, and he's stranded on Mars. They left him there thinking he'd died. And he has to figure out how to cope to get back to Earth. So, and it's a really compelling story. But why I raised this and why I perked up is that there was no communication device. It's completely wiped out. So there's no way he could communicate back with Earth. But for some reason, this guy must have complete knowledge of all of history. He knew that there was a Mars Pathfinder that had landed on Mars and was left there. And the Mars Pathfinder, which is the project I'm talking about, had communication facilities to take it back to Earth. So he was able to move from a location, his current location, I don't know, let's say 50 kilometers, to this new location where the Pathfinder was, and be able to set up communication and then get back to Earth. So that was an interesting thing. And if you have a chance, I really recommend the movie. All right. So because of the limitations I said on the power system, it had to get moving and start doing all these tasks simultaneously. It had to walk and chew gum at the same time. It has to be able to drive to wherever it wants to drive while it's performing other tasks. So as it began the mission, even though every single task it tried worked perfectly, when it started to run them simultaneously, a reset occurred. All Earth knew is that a reset occurred. There's this poor Pathfinder rover up on Mars. Something bad happened. And so they thought, well, now we have to wait 24 hours to do a reboot. They did, and tried it again, and it failed a second time. And then they went through that cycle again, and it failed a third time. So the first and second time you think maybe it's just the harsh Martian environment, something has happened. Maybe on the third time you think that a Martian has actually come and is messing up with our rover. But they panicked, obviously, and were desperately trying to figure out what went wrong. And it wasn't until July 17th when they finally identified what the actual problem was, why these resets were occurring. And then they were able to solve it one day later. And so the question is, well, so what went wrong, and how did they fix it? Well, many of the tasks on the rover, they don't really have real-time requirements, but some do. And so the whole system was set up according to this 1973 Lewin-Leyland theory. However, there's one thing that was unaccounted for. I had mentioned before during the alert that these tasks are supposed to be independent. They don't interact with each other in any way. But it turns out some of these tasks did interact with each other. And so the Lewin-Land theory does not apply in those cases. In particular, there was a high priority, frequently running task which kept at what's called the information bus. But basically what this is a piece of memory. It's like a blackboard in memory. And various other tasks would write information on this blackboard like a database. And other tasks could read the blackboard to get that information and use it as far as their task goes. When something is writing on that blackboard, the maintainer of this high priority task has to step aside so they don't interact with each other. So there's a blocking effect, and you let the write continue, and then the other one comes back in. This maintainer task was considered to be very high priority and ran very frequently. And so when it failed, if it missed its deadline, the system shut down. And that's what was actually causing the resets. The actual situation that happened is you have this low priority task. It was a meteorology task. It was posting meteorological information. So they have this low priority task that's operating, and at some point it wants to write its information on the blackboard, and it starts to do that. When the high priority guy comes in and wants to do something, and it does something, but it has to be blocked or stopped until the low priority guy finishes. So that's a nuance that has to be accounted for. But what really happened is then a third intermediate guy appears, knifes in. It's higher than the low priority guy, and so it just merrily waltzes in, and it can go forever. It doesn't go forever, but it goes long enough to blow the deadline of the high priority guy. So this kind of interaction is what was causing all the resets. Now, that really says what I just said. In the middle bullet, we call this a phenomenon called priority inversion, where a middle guy is actually blocking a high priority task, even though they have no relation with each other at all. And this has never been considered in the Lewin-Land theory. So now the question is, great, now we know what the problem is, but what are we going to do about it? You know, Lewin-Land doesn't apply, and the Mars rover is, surprise, it's on Mars. So what are we going to, we're not exactly going to fly to Mars and do a service call. Now, often in science, theory is driven by observed phenomena. You observe a bunch of phenomena and then you work on a theory to explain it. So, I mean, but that it turns out not to be the case in this case. It turns out that actually the theory to cover this case had actually been invented 6 years before. It was this, you call this a synchronization problem. This priority inversion interruption conflict was actually the subject of a PhD thesis of a student of mine, and it actually came out as a book. So the solution was completely well known, how to do this. We never knew that it would apply on the Mars rover, but nevertheless it did apply perfectly. And the solution is simplicity itself. When you have a low priority guy blocking a high one, then at that moment it has to elevate its priority up because it's now blocking something at a high priority. It has to itself momentarily elevate its priority, run at that high level, and it blocks everything else that could come in and intervene. It's very complicated to work out all the details of this, but nevertheless the ideas are really simple. So the question is, great, we know what the solution is, but what are we going to do about it? Because it apparently requires a modification of the system. So we have this protocol that was developed in that PhD thesis. And the third author, another student of mine, Louis Shaw, went on a literal crusade. He was just compelled to do this. He visited in the US, all the vendors of real-time software, It's a special category of operating system software, not like Windows or you know, any of the Apples. This is software that's designed to deal with real-time applications. He went around and visited every single one of this and was convincing them that this simple problem could befall you, and the solution was really simple. So you know, you've got to put this in your operating system. And slowly everybody complied, with the last domino falling finally with a company called Wind River, which had a product called VxWorks. And that happened to be the operating system for the Mars rover. So miraculously, it turned out that the rover's operating system actually had that protocol in it. And so now you say, that doesn't make any sense, because if it had the protocol in it, why did this reset phenomenon ever take place? Why the resets? And maybe the theory is wrong. Maybe they found an error in our theory. But actually, the solution is really simple. The rover was actually launched, and the software switch that was set for using this priority ceiling protocol was set to off. And so it had the facility, but it had been turned off. So, and the resets happened. So the question is, well, how are we going to turn it on? It's not just a reboot that turns it on, because it's a modification of the actual implementation of the operating system. But the Jet Propulsion Lab engineers actually, almost on a whim, decided to, in the system, launch with it like a debugger as well that you get as a byproduct of the operating system. And they actually launched that as well. And it was that decision that actually saved the day, because from the ground they were able to write a program that the operating system would interpret and change itself. And they changed this priority ceiling protocol from false to true. And then the system rebooted the system, and it went perfectly. It actually exceeded 30 days. And if you Google Mars Pathfinder, it's really great, because you can still see all the photos on Mars. It really was a huge success. But those intervening 12 or so days was a feeding frenzy for the media about the brilliant story gone bad. So suddenly, but at least it got turned around. So on that note, I want to switch topics to driverless cars. Let me speed up a little. And the first thing I would mention is this is really all the rage. And there's a very interesting article in the recent Fortune magazine. It's called "The Ultimate Driving Machine Prepares for the Driverless World." And the head of BMW's Advanced Technology Group, they note that the biggest disruption in transportation since the car displaced the horse-drawn carriage, is now upon us. And the next 10 years will bring more change than the last 30. So the major transformation can be divided into three elements. Autonomous driving, which I'm going to talk about in a minute. Electrification, this is electric cars as opposed to gas-powered vehicles or diesel-powered vehicles. And car sharing, which is like Uber, if you have Uber in Doha. So why autonomous vehicles? If you look at a World Health Organization report, the deaths from automobile accidents globally is 1.25 million, which is 17.4 per 100,000 inhabitants is the rate. In the US, it's 34,000, and the rate is 10.6. In Qatar, it's 330 deaths by accidents. This is in maybe 2014 or some year like that. That's 15.2 per 100,000 per year. So death by automobile accidents is a serious problem. 34,000 and 330 are not getting you to 1.25 million very quickly. Where are the big numbers? Well, the big numbers are in China, which is 300,000 or so, and in India, which is another 300,000 or so. So some of those countries have very, very high accidents. In the U.S., there are an enormous number of accidents caused by drunk driving, cell phone use while driving, texting while driving. It's just very much out of control in the U.S. It's sort of bad behavior. Commuting and traffic delays are expensive in time and energy. And to me, one of the most important things is senior citizens and disabled who are housebound because they're either incapable of driving, or at least they're incapable. They may drive anyway, which is a whole other set of problems. But there's a loss of independence, and it's really a dramatic change in someone's lifestyle if they can no longer drive, at least in the U.S. And I measure in Qatar as well. So automated vehicles are going to change the face of transportation. There are huge challenges, technology challenges, the uncertainty of the world, weather, road conditions, construction. The equipment that's driving the car can fail. And they're interesting, when cars are talking to each other, it's possible that you can have malicious hacking in the cars. So security is another issue. And then this is a whole new area for legality, regulations, insurance. We haven't begun to see it. And probably the most the interesting problem is how to get from here, where there are essentially no driverless cars, to there, where everything is a driverless car. Imagine the intermediate state where some cars are driverless and some have drivers, and the kind of chaos that situation may have. There's another point I didn't make, but in driving around Doha with this incredible transformation of the infrastructure, in 10 years or so, where driverless cars are really going to start to become prevalent, highways have to change as well. If we had full-scale driverless cars, you can have narrower lanes, you can have more dense traffic patterns, you can have much more efficient transportation. And cars will talk to traffic signals, cars will talk to each other. And it will be a whole new world. And the question is, when you're now laying down a new infrastructure, are you taking into account what the changes are that are actually not that far away? So I'm going to do this anyway because I wanted to, what I hoped would be a treat for old-timers at Carnegie Mellon Qatar campus. The slide says that the CMU has been big in autonomous vehicles dating back to 1984. And I'm going to take a sojourn for about 30 seconds. The narrator on this is somebody that a few of you knew called Chuck Thorpe. He was the director of the Robotics Institute. And there's a film, a YouTube video, about the CMU Robotics Initiative.
Centimeters per second.
Let's see if it works.
The Nav Lab, built in 1986, was our first self-contained test bed. It had room for onboard generators, onboard sensors, onboard computers, and, most importantly, onboard graduate students. Researchers riding on board were in a much better position to observe its behaviors and to debug or modify the programs. They were also highly motivated to get things working correctly. The latest test bed is the Nav Lab 2, an Army ambulance Humvee.
That the guy, the fresh-faced graduate student, was actually Chuck Thorpe, if you recognized him or not, who was madly kind of steering this thing. I cite that because this vehicle used to, it seemed to be driving at about 2 miles an hour along a path in Shenley Park, if you're familiar with Pittsburgh, often outside my window, my office window. So I saw this happening many, many times. And it would, so to speak, sometimes climb a tree, meaning that it was running on an asphalt path in Shenley Park, and when the sun was shining, which is sometimes it actually does in Pittsburgh, you could see a shadow of the tree, And in these early days, the vision system was so poor that it couldn't distinguish between the path and the tree, and it would sometimes, quote unquote, climb a tree. It would veer off and follow the shadow of the tree and then could be completely lost. So we've come a long, long way from the early days of autonomous vehicles. I will show you, Google is the most aggressive. It's called Alphabet now, but they have a subsidiary that's doing driverless cars. This is their driverless car. It's driving all around every day in Mountain View, California area, in the Silicon Valley area. It's kind of ugly. It has this awful looking device on the top, which is critical to it for its sensors. And on February 14th, which is Valentine's Day, there was a headline that this Google car actually caused an accident. It's the first recorded instance of a driverless car actually being the cause of the accident. There have been others have hit the driverless car, but that was not the car's fault. It actually did have one. This is the current CMU car. It's Cadillac, and it doesn't have any real visible sensors on it. The sensors, here's the suite of the sensors and where they are. LiDAR is a kind of a mesh of light and radar. It's lasers doing radar-like activities. They're cameras, GPS devices, and radars, wheel speed sensors, and so on. So it's loaded with sensors. And this is a visualization of the data that's coming in that it's gathering as the thing goes down the highway. This is the spare tire well, and that's where all of the computing equipment is living in this Cadillac. And I obviously don't have time to go over any of this, but there are many, many tasks that have to be done. There's scanning tasks. It's continuously gathering data. The data has to be processed. You need to do image recognition. You need to determine if there are obstacles. You need maps. You need to plan a mission. You need to plan your own motion. You have to actuate and decide what speed you want to drive and the like. There are many, many tasks in here that are all interrelated. And this is a classic kind of real-time problem because many of those tasks must meet deadlines. In terms of research and development for the Carnegie Mellon car, and we suspect most of the other ones as well, it's back to this kind of Lewin-Leyland periodic scheduling problem. So in some sense, we have a handle on how to deal with the scheduling to meet those deadlines. And right now, there are many, many big-time research efforts going on in driverless car areas. At Carnegie Mellon, there's a major one. It's funded by General Motors Corporation. Apple is, nobody knows what Apple is doing except we know they're designing an Apple car, whatever that means. But Audi, BMW, Ford, GM, Honda, Mercedes, Nissan, Tesla, Toyota, Volkswagen, the car companies are completely all into this because this is going to be the future. Let alone and Google, of course, and then Uber has a big research outfit now in Pittsburgh to be newly located at Carnegie Mellon. How soon will this happen? Google predicts 5 years. 5 years ago, they predicted 5 years, so you know what that's worth. I asked Raj Kumar, who is the head of the CMU effort, and he said he thought realistically 10 years was a reasonable target, where we're really going to see this go onto the road. Simultaneously, there are major research efforts going in on the highway of the future, which is to design the idea of what a highway should be in the advent of driverless cars. Time frame is uncertain, but what is not uncertain is this is probably I expect it to be in my lifetime, and I'm probably the old guy in the room, so I expect everybody in this room is going to be alive in an era that's driven by that's dominated by driverless cars. And we need to prepare and consider building infrastructure to support this. Okay, the time is marching on. It's coming onto the public mind. This is IEEE Spectrum, which is a magazine associated with the IEEE. The cover is suppose that in 2023 a driverless car for the first time kills a pedestrian. A lawsuit is sure to follow, but exactly what law will apply, nobody knows. So there's a whole uncertain future ahead of us to try to work out what this is, but there is an inevitability here. 10 days ago in Sunday Comics, what do you mean you're just cruising? Get back here immediately. He says, I have one of those self-driving cars, which is out cruising somewhere. So it's very much in the public's mind. A new theory is needed. There are other issues. In Mars rover, it was the lack of independence that came into play that had to be dealt with. Fortunately, it was. In the autonomous vehicle, everything is periodic, but it turns out the execution times of these tasks can vary, and they can be exceptionally long. And you've got to do something about that. So there's the idea of stochastic execution times has come on the scene, and we're going to have to build a new theory, build that into the theory in order to deal with it. And these stochastic execution times are then connected with the next problem I want to talk about, which is video streaming, where a new theory is needed to be able to deal with the stochastic behavior. In the case of video streaming, it's a couple things. First, the providers want very high efficiency. They want to be able to maximize the number of customers they can deal with. So the 69% is too low a number for them. They want to be at much higher utilization levels. But there's also stochastic behavior that needs to be dealt with in the video streaming. So let me jump to that, and I just want to, these are more dominated by pictures now. Here's an old graphic that I have, which is there was a record of the transmissions of a video conference that took place over about an hour time period. And then in that video conference, we kind of cut and paste pieces of the video conference together to give you some idea of what it looks like. So in a video conference, you need to transmit frames of information. The camera is taking pictures of what's going on and transmitting it over an internet to somebody else to see. And normally, they don't transmit the picture itself. They transmit the difference in the picture from its predecessor, because usually they don't change very much. Particularly in a video conference, you're just kind of sitting around, and from one number of milliseconds to the next, not much is different. And in the case where it's relatively quiet, you can see this is the bandwidth needed to transmit that information is pretty low and not so variable either. And it's down around a 500 kilobytes per second level. When there's some activity, like somebody's walking around the room, or a person is choking somebody next to them and they're thrashing around, whatever it may be, there's some action going on, you can see more variability and a bit higher level of bandwidth needed to capture this. The differences from frame to frame have more content. And then when the camera is actually moving, then like everything is changing constantly, and so you have this super amount of variability. It goes much, much higher. All right, so let me look at the next one. Now, if you put this whole composite together in terms of like a density, mostly you can see down here, this big hump, says that most of the frames that are transmitted are down around the 500 level. Sometimes less, sometimes a little bit more, up to 1,000, but most of the frames have that amount of information that needs to be transmitted. But notice there's this very long tail. It goes all the way out to almost 6,000. So the difference between the worst case, 6,000, and the average case, which is probably back here a bit below 1,000. It's like a 6-to-1 difference. If you follow the Lewin-Leyland theory, you have to take the worst case. You're going to say, what's the worst that could ever be? Well, okay, it's 6,000, good. But on average, you'll just waste all that because you don't need that much. So there are deadlines in this context because you need to have continuity of the image. Okay? You don't want it to stall and then jump ahead and stall and so on. It's a very poor experience. But the trouble is that to take this worst case point of view is to dramatically underutilize the system if you're really going to do that. Okay, so let me just see if I can gain some time here. Fortunately, at least in these video conferencing, they turn out to be what are called not hard real time. It's not absolutely imperative you meet these deadlines. They're what are called soft real time. Because actually, if you miss a little bit, a human perception system will just fill in the gap. Sometimes the perception system isn't acute enough to be able to even see that you've lost some information. And so what you want to do is to take advantage of the ability to drop some information now and then and run as high as you can in capacity so you can handle as much information as possible. And this particular framework is falling into another branch of probability theory called heavy traffic queuing theory. And I just want to say a word or two about this, some graphs. A queue, again, just think of it as a waiting line. Think you're in passport control. There are customers arriving, and there are customers getting served. And if you look at the rate at which work is arriving, it better be less than 100%, otherwise the server is saturated. And basically when this traffic intensity, which is a measure of how heavily utilized the system is, when the traffic intensity is low, which is 40%, this is a graph which just is continuously taking snapshots of how many are in the system. And you can see this really dark area because mostly 60% of the time, 1 minus that row, is the fraction of time that it's idle. The system is idle. And so you can just see it's kind of back and forth and back and forth. Not a very interesting picture. If you raise this traffic intensity, this is a 60% picture. It's a little different, but not a lot different. The scale, you probably didn't look at the scale. It's double what it was before. The peak before it was 7, now it's up to 16. But basically, it's all sitting down around 0. And these are kind of useless plots. There's almost nothing to see in them, except you know that you used a lot of toner in the printer, and you probably need to replace it after you've printed a few of these. But if you go up to a high traffic intensity, this is 95%, a whole new life form takes over. And you may not, there's no reason you recognize it, but at least in seeing this picture, you can see there's a qualitative difference to what's going on. It's sort of a life. It hits 0, but then it takes a sojourn away, and then eventually comes back, and so on and so forth. It turns out that this is one of the really lucky situations that at high levels of intensity, this queuing system is modeled by what is called a Brownian motion. Brownian motion named after Robert Brown, who's a biologist who, if you had an elementary biology class, at least in my era, you probably learned about Brown, who had a cell theory of biology. And he was observing the movement of dust particles trapped in pollen grains in 1827. It's also known as the Wiener process, named after Norbert Wiener, again a famous mathematician. But this is probably one of the, close to the most studied object in probability theory. This has been around, and you can buy books, believe it or not, almost 1,000-page books, which is like facts about Brownian motion. So it's huge literature on this. And in '63, John Kingman, a British probabilist, proved that in fact queues if you have them in heavy traffic, meaning this traffic intensity is going up near 1, they behave like this Brownian motion. And so we can make extremely accurate predictions about the behavior of these systems in the high-intensity world. The trouble is, and I see I'm over time, so let me see if I can do this briefly. The trouble is that this does not work for the real-time problem. This is the same graph 2 slides ago, the same Brownian motion looking thing, but I dropped an arbitrary line at 30. So this form crosses 30 here and there. The number 30 is kind of irrelevant here. But every time it crosses 30, it means there are 30 customers. And those 30 customers have 30 deadlines. And we're interested, not just that there are 30 customers, but we want to know, are those deadlines going to be met? And the trouble is, it would appear that you'd need to know what every one of those deadlines is, because over here there are 30 customers, then there are a different 30, and then there are different 30, and then over here there are different 30. And so in order to track the behavior of the system, you have to track explicitly what those numbers are. And that's a killer, absolute killer, because the modeling then goes up into high dimensions, and that's only with 30, and may have 60, and then it's even worse. So the dilemma is we want to have a model that permits stochastic behavior and actually takes these timing requirements into account. But we don't want to have so much detail in this model that it's unworkable. So fortunately, what the work we've done here is built on this idea of heavy traffic queuing theory, but it's been augmented to take into account deadlines. And I just will show you a picture or two. This is a screen. These are a couple of screenshots from a simulation application. And what happens is it's just a queue, and customers are arriving with deadlines, and they're processed by some scheduling algorithm, and then they leave. I just let this thing run and stopped it. It happened that there were 83. We'll maybe learn why it's 83 in a minute. So at the moment in time when I stopped it, by the way, the system was servicing these tasks using what's called processor sharing, which means at this moment in time there are 83 customers in the queue, and each one is getting 1/83rd of the processing power. So it's kind of slowly as a mass being processed. And here they're depicted on this. This is the one. This, in terms of what their current timing requirements are. This one is 25 time units late. The one that's passing right through 0, its deadline is just elapsing. The ones up here, they have plenty of time, it would appear. So this is an example. You can see a huge amount of lateness going on. This processor sharing is not paying one whit of attention to the customer's deadlines at all. And as a result, a massive lateness is occurring. Okay, but the point I want to make is that you can actually predict what this 83 customer picture will look like. So if I show you the next picture, this is what the theory tells me, that if you have 83 customers with these characteristics, these random characteristics, and you're using processor sharing, that's the functional form that their deadlines will take. And you can predict exactly how many. It's almost 50. The line is crossing through the 50% point. It means half of them will be late at that point. Yeah, I know. I'm getting the hook here. If, in fact, you were using first in, first out, you weren't, so the two aren't matching anymore, but the form would have had this picture. You can see it's moved over to the right, which means there's less lateness. Only 40% would be late, and the latest one would be late at 10, whereas this one's late at 25. If you were using earliest deadline, which is the optimal thing to be doing in this case, the picture looks even better. The form moves all the way over, and you can see that at this level of work, 83, this customer is just about to go late. Okay? in other words, if you can tolerate up to 83 customers, but the 84th is going to put you over the edge and you're going to start to see lateness. So you can identify exactly how many customers you can let in the system and be able to survive without any lateness. So let's see, Oker, how can I finish up quickly? There's a very precise formula which predicts how much lateness there will be, and it says if you take the log of the probability of lateness, it's a linear function of the mean deadline. And here is a graph which it says the prediction is almost perfect. The three different lines are three different levels of variability in terms of the amount of processing time it takes to do a task. Down here, tasks are deterministic. Here, tasks have what's called an exponential distribution, which is fairly random. Here, we took data from all of the packets going out the CMU pipe onto the internet. You use that as a distribution. It's way more variable, and you can see that there's more lateness, but it fits in this perfect linear picture. So we actually have control about how to deal with this stochastic phenomenon, and hopefully a lot of this will get embedded in these kinds of streaming applications. I think I can probably stop. Let me have a couple of slides just to say that there's always more work to be done. There are new phenomena you have to deal with. And the big thing we find is the hardware architecture is running way ahead of what we can do theoretically. Probably if any of you brought your relatively new computer with you, then you have multi-core architectures, which means you have multiple processors on a single board. The work we've done doesn't apply to that, so we need a whole new theory to deal with new hardware architectures. And the latest technology, like the new airplanes, want to use the latest computers and need to get FAA certification for commercial aircraft. So we're going to have to work quickly on the theory to be able to handle new technology. So that is actually the last slide, Oker, and I'll be happy to stop. I'm sure I've burned our time for questions, but thanks very much.
Some of you have to leave at 1 o'clock. Feel free to do so.
You're late then.
Questions? Any questions?
You missed your day.
Any questions other than when lunch is being served? That's at 1:30.